Hello Math 119 students. In this video I want to demonstrate chapter 7, which goes over the central limit theorem and sampling distributions. So I'm going to demonstrate a sampling distribution, and then the central limit theorem has to do with sampling distribution, so then we'll demonstrate the central limit theorem. So we'll learn what a sampling distribution is, and we're going to take the sampling distribution of the sample mean. And then we're going to learn the characteristics of the sampling distribution of the sample mean. So let me demonstrate. Let me start the simulation. So with this I'm going to begin with a bell-shaped distribution. So let's take the distribution for the heights of men. So the heights of men are thought to have a mean of 69.5 inches, and the standard deviation is thought to be 2.8 inches. So let me move this over. So here's the population distribution for the heights of men. So now what I want to do is I want to take a sample of size 2. Okay, so if I take a sample of 2 men, just as if I randomly sampled 2 actual men from the population, but we're going to do it by simulation. So let me do this one time. So we simulated as if we selected, looks like one of the men had a height of about 68 inches and the other one around 69 inches. But the important thing is that the mean of our sample is 68.7 inches. So here's our first sample mean. And now we can do the same thing over again. So here's our second sample. It had a mean of 72.2 inches, about 6 feet tall. Now, if I want to, I could do this 5 times. So what I'm doing is I'm repeatedly taking samples of size 2, and for each sample, I'm calculating the mean. This is what we mean by building up the sampling distribution. So now I'm doing this 5 times. Okay, now we have 7 samples. Our last sample, the mean was 67.96. And the mean of our 7 samples, that's what it tells you on the bottom. It tells you that we have 7 samples, and the mean means the mean of the 7. So this is the mean of the means. Also gives you 1.807 is the standard deviation of the 7 means. Okay, now I'm gonna jump ahead and do this 1,000 times. So we're gonna take 1,000 samples, and for each sample, we're gonna calculate the mean. So here are the 1,000. Now we have 1,007 means. Here's the distribution of the 1,007 means. So now I want to actually get 5,000. So now I have 5,007 means. So here's the distribution of the 5,007 means. So let's look at 2 things. One, let's look at the mean of the 5,007 means, the standard deviation of the 5,007 means, and the shape of the distribution of the 5,007 means. So the mean is 69.5. And so you may notice that the mean of the 5,007 means is almost identical to the population mean. Okay, that's not a coincidence. That should always happen. And then the standard deviation is 2.0053. Okay, so let's remember that. 2.0053. That's the standard deviation of the 5,000 means. Okay, here's what I'm going to do next. I'm going to do the same thing, but I'm going to reset it and increase the sample size to 30. Okay, so now we'll have a sample size of 30. Let me take one sample. So we took one sample of 30. The mean was 68.993. Okay, let me jump ahead and take 1,000. Now I'm going to take 1,000 samples of size 30. Each time I'm going to calculate the mean of the sample, which has a size of 30 now. And now we have 1,001 means. Here's the distribution on the bottom of the 1,001 sample means. Okay, so you can see it has a much narrower distribution, but it still looks fairly bell-shaped. So now let me jump ahead and take 5,000. Now we have a 5,001. So let's look at the three main characteristics. What's the mean of the 5,001 sample means? What's the standard deviation? And then what's the shape of our green graph, which gives the green graph is actually gives us an idea of the shape of the sampling distribution. The sampling distribution is the distribution of the sample means. So first of all, the mean is about 69.4967, very close to 69.5, which is the population mean. The standard deviation is 0.508. Okay, that's the standard deviation of the 5,001 means. And then notice the shape. The shape looks bell-shaped to me, but it's a narrower bell than when we had a sample size of 2, much narrower. Okay, so now let's compare this to what the central limit theorem tells us should happen. Okay, so the central limit theorem in number 1 says mu of x bar is the mean of the sampling distribution. Well, the mean of the sampling distribution should equal mu. Mu is the population mean. So remember, mu is 69.5. Mu of x bar was the mean of the 5,000 means, and they were both very close to 69.5. And then it also tells us that the standard deviation of the sampling distribution should equal the population standard deviation divided by the square root of the sample size. Okay, so for a sample size of 2, remember the population standard deviation is 2.8. 2.8 divided by the square root of 2, I calculated that with my calculator, that's 1.98. And in our first simulation, the standard deviation of the 5,000 sample means with the sample size of 2 is 2.0053. Well, that's pretty close to the theoretical value of 1.98. And then when we increase the sample size to 30, 2.8 divided by the square root of 30, that's 0.51. And the mean of our 1,001 sample means was 0.508. So that's pretty close to the theoretical. And then another thing about the shape, number 3 tells us about the shape. So number 3 says the shape of the sampling distribution, that's the green distribution, should approach that of a normal distribution. Well, in both cases, we had pretty close to a normal distribution. So now let's look at this chart we have here. So we had a normal distribution for our population. Then when we had a sample of size 2, the shape of the sampling distribution was a bell, but it was more narrow than the population. But and then when we increased the sample size to 30, we had a much narrower bell. But in both cases, we had a bell-shaped distribution. Okay, so I want to stop this here, and then in the next, I'll make another video where I will do a simulation for when the population has a uniform distribution, as it does here, and a skewed distribution, as it does in the third one. Okay, how do we stop?